Hi everyone, Charles here for MLE Papers. Over the past 10 years, the field of reinforcement learning, or RL, has given rise to some of the most interest-catching applications of the recent years. 2015, Google DeepMind releases its RL algorithm AlphaGo and defeats a pro-human at the game of Go. 2022, the world is taken by storm by ChatGPT, which itself integrates RL-based mechanisms. And this month, March 2025, RL founders Richard Sutton and Andrew Barto became the 2024 awardees of a Turing Award, which is the equivalent of a Nobel Prize in computer science. They will officially receive the award during the ACM banquet, which will take place on Saturday, June the 14th, 2025 at the Palace Hotel in San Francisco, California. But who are Sutton and Barto? What is RL and how does it work? And how can you learn RL? Is there a best book or additional resources? So many questions that we will answer in today's video. But before that, I would like to mention that I have interviewed on this channel RL researcher Amy Zhang, assistant professor at the University of Texas, Austin. She does an amazing job talking about research and giving advice on how to navigate through the world of research and academia in general. The link will be in the description box down below. Make sure to check it out at the end of this one. Whether you're a student, an enthusiast, or a professional in machine learning, let's enjoy the next 10 minutes to discover or rediscover the field of reinforcement learning from its foundations by Sutton and Barto to its latest applications today. Sutton and Barto's lives. The story starts in 1970. That year, a student named Andrew Barto received a Bachelor of Science in Mathematics from the University of Michigan, Ann Arbor. Andrew read some foundational works on brain neural networks, including this foundational article by McCulloch and Pitts, which inspired Hinton and Hopfield 2024 Nobel Prize in Physics. Inspired as well by such readings, Andrew decided to undertake a whole new challenge: use computers and math to model the brain. Just that. With his objective in mind, Andrew Barto then pursued a PhD in computer science, which he obtained in 1975 from the same University of Michigan. In 1977, he joined the University of Massachusetts Amherst, which has never left until today. 1 year later, in 1978, a student who just graduated with Bachelor of Arts in Psychology from Stanford joined the University of Massachusetts Amherst. This student is Richard Sutton. He has read the works of Harry Klopf, and he is convinced that standard supervised learning techniques are not enough to understand intelligence. Instead, he thinks that intelligent behaviors learn by trial and errors. Richard Sutton and Andrew Barto have very similar views and insights on why existing supervised learning models aren't enough, and why a new framework is required in order to explain intelligence. This naturally leads Richard and Andrew to start a long and fruitful collaboration. Under Andrew's supervision, Richard pursues a master, a PhD in computer science, and even postdoctoral research until the end of 1984. Their unstoppable collaboration and work together at that time gave birth to the field of reinforcement learning. They even wrote a book together called Reinforcement Learning: An Introduction, which they released in 1998 and is widely acknowledged as one of the greatest entry points to the field, but more on that later. In 2003, Richard Sutton moves to Canada and becomes professor at the University of Alberta, position which he still holds to this day. In 2017, he becomes co-founder of Google DeepMind's first international AI research office in Edmonton, and occupies the role of distinguished research scientist until the office's closure in 2023. Historically, reinforcement learning has been brought to fame, in part thanks to the algorithms AlphaGo and right after it AlphaGo Zero, which defeated the world champion at the game of Go, Lee Sedol, in 2016. RL has further been integrated into many of modern large language models, including ChatGPT, under the form of RLHF, reinforcement learning with human feedback. And it is widely acknowledged as one of the fundamental areas of AI and machine learning today. But what is RL exactly? Before we answer that question, if you enjoyed this video, that would be awesome if you could give this video a thumbs up, subscribe and hit the bell icon to get notified of the next video. That's completely free for you, and it really supports all of the work that I do for you for free on this channel. Thank you so much. And now, RL basics, MDPs, and Bellman equations. RL studies the interaction of an agent with an environment. You can think of that agent as a video game character who is in a certain state and takes an action yielding them a reward and teleporting them into a different state, and so on. Formally, assume that there is a finite number of states from 1 to S and a finite number of possible actions from 1 to A that our agent can do. At every time step t, the agent is in a certain state, st, here equal to 1 on the screen. Then the agent chooses an action, at, here it is action 2. The choice of action 2 in state 1 yields a reward, rt plus 1, and teleports our agent to the next state, st plus 1. The reward state pair, rt plus 1, st plus 1, is generated by probability distribution, p given stat. Here this yields the reward rt plus 1 equal to 0.5, and the next state st plus 1 equal to state s. And this process is repeated, potentially many times, until we finally reach a so-called termination state. In our case, it is state s-1 with the key inside. Importantly, the joint probability distribution which generates the reward and the next state depends on the current state st and the last action chosen by the agent at. The model, which captures all of that, the states, the actions, the probability transitions, and potentially random initial state, is called a Markov decision process, or MDP. Now, assume that the agent's decision process can be represented by a probability distribution pi. In other words, at time t, the agent chooses at is equal to 1 with probability pi of 1 given st, at is equal to 2 with probability pi of 2 given st, and so on. We define the value function, v pi of s, as the discounted cumulative reward of the agent starting from state s. We also define the q function, q pi of sa, as the discounted cumulative reward of the agent starting from state s and whose first action is a. Now, as a first remark, we may be wondering, what is that discount factor gamma, and why do we need it? This discount factor decreases the importance of the later rewards. At each new time step, the reward is decreased by factor gamma. One of the main reasons for it is that the sum of the rewards might have an infinite number of terms. So we add that discount factor, which strongly decreases the terms of a sum, such that it becomes finite when the rewards are between 0 and 1, for example. But naturally, the number of terms of a sum is guaranteed to be finite, as is often the case in bandit problems, then we do not need it. Now, interestingly, the value function and the q function are intrinsically related. Let us start from the value function at state s. With probability pi of a given s, the agent located at state s chooses action a, and their expected discounted cumulative reward from there is q of sa. This yields a first formula expressing the value function as a convex combination of q functions. Now let's look at the q function at state s and action a. That state action pair yields the reward r prime and the next state s prime with probability p of r prime s prime given sa. The agent then incurs the reward r prime and a value function starting from state s prime one step later, and thus discounted by gamma. This yields the second formula expressing, this time, the q function from the value function. Those two equations are called Bellman equations and are the cornerstone of reinforcement learning. Learn the value function and TD0. For example, assume that you know all the probability transitions. How do you compute the value function of a given policy pi? Take the first Bellman equation, it gives you v pi of s, but you don't have q pi of sa. No problem, you use the second Bellman equation and replace it in the first one, which gives you a set of s linear equations in v pi of 1, v pi of s, so you can solve it, and voila! Now, what if solving the system is too computationally heavy? You can start from any function v0. The update rule helps to define a function v1 from v0. Then we can derive v2 from v1, v3 from v2, and so on. And the sequence of functions we just derived converges to the true value function v pi. Now, what if we don't know the probability transitions? Instead, we run the policy pi and observe a sequence of states, actions, and rewards S1, A1, R2, S2, A2, and so on. Now, how do we estimate the value function of the agent's policy pi? Assume that we are at state st and that you hold an estimate v hat of s for every state s. How are we going to update those value function estimates? After choosing action at, the agent receives reward rt plus 1 and reaches state st plus 1. Now, this yields another estimate of a value function at st, precisely the first reward rt plus 1 plus the empirical value function from state st plus 1 discounted by a factor gamma. The gap between this new estimate of v hat of st and the former one will be used for the update rule. Precisely, the new estimate of a value function at state st adds to its old value v hat of st the gap that we computed. This gap is scaled by the constant alpha between 0 and 1, which measures how conservatively we make the update. At the one end of the spectrum, the ultra-conservative choice, alpha is equal to 0, means no update, while the anti-conservative choice, alpha is equal to 1, means an update which is extremely sensitive to the first observed reward, rt plus 1, and therefore makes the value function unstable. This method is called TD0 and belongs to the broad class of temporal difference methods, which have been notably introduced by Richard Sutton in 1988. Go further in RL. Now, if you want to know more about reinforcement learning, I have made one video on a phenomenal research paper from this year, which studies the burning time of finite time-dependent Markov decision processes. If you are curious about what is being done in state-of-the-art research in reinforcement learning, make sure to check it out. It is only 10 minutes give or take, and it is self-contained. The link will be in the description box down below. Now, beside the video, there is one specific textbook that I would like to recommend. It is called Reinforcement Learning and Introduction, and it has been written by, guess who? Richard Sutton and Andrew Barto, are two Turing awardees of this year. I'll be talking specifically about the second and latest edition of this book, released in 2018. This book is divided into 3 parts. The first part is a friendly introduction to RL. Starting from the definition of a Markov decision process and Bellman equations, it covers all the basics of a field, including dynamic programming methods like policy and value iteration, Monte Carlo methods, as well as the temporal difference method TD0 that I quickly introduced today. The second part of the book applies the ideas of the previous one to function approximation, and hence incorporates many machine learning methods like neural networks, kernel methods, gradient methods, and so on. Finally, the third part of the book examines the connections between RL and other fields like psychology and neuroscience. It further includes some case studies of RL applications, including Atari games, backgammon with TD Gammon, and the game of Go with the celebrated algorithms AlphaGo and AlphaGo Zero. There are several exercises dispatched across the whole book that I naturally encourage you to try, should you settle for this one. The prerequisites to read the first part of a book are minimal. You only need to know the basics of probability, like the notion of the expectation of a random variable. Arguably, a young undergrad with enough motivation should be able to follow without much trouble. Now, the second part of the book is more advanced and requires the same math background as an introductory machine learning textbook. And that is a little more statistics and probability, some linear algebra and matrices, and some differential calculus. In particular, be comfortable with gradients and partial derivatives. Now, what are the pros and the cons of this book? First thing, this book is an absolute reference. Most machine learning researchers have read it and all have heard of it. Now, while the fact that your neighbor read it might not be the most valid reason to read it yourself, its content is considered as fundamental knowledge by all of the RL folks, and most of the RL friends that I have literally quote it. So if you want to get into the field of RL, you'll have to master its content by one way or another, be it with that book or with another one. Second pro, this book is extremely clear and well written. If we think about it, the RL setting is notation-wise extremely heavy. The sheer notion of MDP implies a state, an action, a probability distribution, a reward, and potentially a time. In that RL jungle, it's easy to get lost, even for the initiated, so I really appreciate the effort and clarity. Third pro, this book is extremely approachable. There are no heavy mathematical proof and no stack of lines of code. The author's focus is on intuition and basic manipulations in order to understand the core concepts of RL. As a consequence of that, this book is readable by early undergrads in their first years of university. And if you understand even part of the more technical videos of this channel, you are more than qualified for it. Fourth pro that I want to mention here, I particularly appreciate the penultimate chapter of the book on case studies, which shows some successful and enlightening applications of RL, like TD Gammon and AlphaGo. Now for me, this book's main downsides come as the silver lining of its approachability. First, the mathematical foundations of the field of RL are barely mentioned. I'm thinking about some basic fixed point theorem which underlies the study of Bellman equations for RL scientists. Of course, this would raise the math requirement bar from early to mid-undergrad, yet it brings some insight that a more curious enthusiast might appreciate. Secondly, it is an introductory textbook, and while it brings a very nice introduction to the field, if you want to get serious into reinforcement learning, some further reading will be required. Overall, this book is a very friendly introduction to the field of reinforcement learning, with no heavy math requirement, while presenting some of the more appealing applications of the field. But as the name suggests, it is an introduction, and some additional material is required if you want to work in that exciting area. As a final point of consideration, this book is also available for free on Richard Sutton's website. Alright, that's it for today's video. If you enjoyed it, please give it a thumbs up, subscribe, and hit the bell icon. I would really appreciate your support. Thank you again so much for watching. I wish you a wonderful week, and I'll see you in the next video. Cheers.